Okay, so how do you come up with the translation, right? So first, we already talked about this. We have something called page offset, right? With 4 kilobytes of a page, we need 12 bits, right? So this is 12 bits from 0 to 11, right? 2 to 12 is 4 kilobytes. This is something that we don't want to translate. So this is something that we'll just copy over when we translate the virtual address to a physical address, because we only translate the VPN, this is a VPN to PPN. Okay. We only want to translate the page. We don't want to translate. Come back to that analogy, right? So the byte is like the single word or single line or single sentence in the page, right? On the page in that book. We don't need to translate, come up with a translation for each line. Okay, address. We don't need to address that. We don't need to have that fine-grained translation to save. I'm going to talk about that, right? So to minimize the complexity, we only want to translate the page number. But how exactly do we translate the page number? So first of all, again, we have a 32-bit address, see here, okay? But the physical address is actually shorter, right? In my example, this example, we have 30-bit, right? Physical address. How large is the physical memory? How large is the MM? You know, I keep asking you the same question, right? So that you guys are more familiar with this, right? This shorthand. 30-bit, how large is the physical memory space? 1, right? 1 GB. 1 GB. 2 to the 30 is 1 GB. Okay. So 30 is 1 G, and our unit is byte, right? It's byte addressable. That's why we write down 1 GB. Okay, again, same question, right? How exactly do we translate? So this is the virtual address, right? Instruction, what program sees, and this is what Howard needs to know, right? The physical address. Okay, and this is sort of a similar, right, to the byte offset for cache, the page offset. Okay. All right, so here's how we translate. This seems like a somewhat complicated diagram, right? If you don't appreciate it right away, this is totally fine. I'm gonna break it down. I'm gonna break it down to steps. But first, let's look at the key things. Again, we want to translate. Ignore the top part first, right? The page table register. You don't need to worry about this right now. Yeah, we want to translate virtual address, right, into physical address. So like I mentioned, we need some kind of a table of contents, right, in the TOC. And that can be just a lookup table, right, or dictionary, or some kind of a yellow book, right? Basically, we just need to have a lookup table somewhere, right, where we can look up the correspondence between the virtual page number and the physical page number, right? If you think about a yellow book, right, the virtual one could be your name, right? The physical number could be the phone number or address, right? The house address. And this is the so-called page table. So these are our TOC, the page table. Then we put the TOC, this page table, in the main memory, in the physical main memory, right? And inside this page table, for this specific case, okay, this is also in memory, right? This is a table. This is something that can be addressed. For this page table, we already know that we have 2 to the 20, right? So if you look at this one, or talk about this, we have 1 million pages for our example, right? So which means that we can use 20 bits to address. So this is where we use 20 bits. We use a virtual page number to address this large table in the physical main memory, okay? And so we have these many entries, right? 2 to the 21 million entries in this page table. Per entry, first, these entries are named. We call them PTE, page table entries. Okay, not the interesting name, right? It's just the entry in the page table. Each entry means each entry is called a PTE. Inside each entry, we have two fields. Okay? The real one is slightly more complicated than that, but the key thing is we'll start adding to some other fields to this one. But for now, only have two fields. One is the valid. Is this a valid PTE? So do we have a valid physical page number or not? And the corresponding physical page number. Okay. So basically we look up, right? We do a lookup, right, on this page table, and then just find the corresponding PTE or the page table entry. And inside this entry, we check, do we have a valid PTE or not? If we have a valid PTE, then we grab the PPN, the physical page number, and concatenate it with the page offset. And we are done. That's how we do the address translation. Any questions about this? So really the VPN, right, the virtual page number, is used as some sort of address to index the page table. That's just how we use the index bits in the, right, for the cache, right, to index a cache location, very similar. But this one, right, this page table is not holding real data, it's holding this address translation, is holding the PPN, right, not the data block. All right, but then you may ask, right, where exactly, right, is this page table? It's somewhere in the main memory, right? If it's somewhere in the main memory, it must have a physical address. So the physical address, again, is a VPN, right, and analogous, right? It's very similar to this this index for the cache, and we have this page offset. Right? One thing I was saying is, right, so we need to know where exactly is this page table. The address of this page table is held in this so-called page table register. We sometimes call it PTR. This is just a special register in the CPU. Okay. If this still not too, right, so if you're still confused, let me try to further break it down, right? So here's the sequence. So first we have this PTR, right, page table register. This one holds the physical address, okay, of the page table, because the page table is somewhere in the main memory, right? It doesn't have to be in the physical address 0. It can be in the physical address 10,000. So if that's the case, then page table register holds an address 10,000. That's a physical address. And from here, okay, we can find, okay, we can index the first PTE, right? PTE 0 with the address of PTE 0, page table entry 0. The address for that one is held in this page table register. That's the purpose of this special register. Okay, so once we know the address of the very first of page PTE 0, we can then combine it, right, with the VPN number. VPN is the virtual page number. Virtual page number, again, in this case 20 bits, right? Since we have 1 million pages, right? So 2 to 20, that's why we have, right? We can use 20-bit, right, to address 1 million entries, 1 million PTs inside this page table. Okay, and this VPN basically tells us the index of the corresponding PTE. And we extract, right, the valid bit is valid, then we extract the corresponding physical page number over here. In this case, we have 18 bits for PPN and concatenate it with the page offset. After that, we are done, right? Now we have the real address. Now we can find the real data from the physical memory. Any questions about this one? About the sequence? Right, so really it's nothing special, right? So what we are doing is just a page table lookup. Okay, Ambrose is asking the obvious question, right? Very good. This is leading to my next slide, right? What if the valid bit, right? What if the PDE? So in this case, right, this is called PDE. I keep saying this shorthand, right? This acronym, so that you guys remember the meaning, the name. This is really the entry in the page table. What if the corresponding valid bit is 0, meaning that the physical page, right, is not allocated by the hardware and OS yet? That's where we have something really interesting. It's a really important concept, which is something that we will take a closer look at in the next lecture. It's called page fault. This is an exception. Okay, so this is where basically the data that we need is not even in the main memory yet. That's so-called page fault. Okay, basically there's a miss in the page table. The miss in the page table has occurred. That's where we will need to spend a million cycles. We will need to spend a lot of time to load the data from the hard drive, from the disk, to the physical main memory. Once we load it, then the corresponding PDE will be set with the correct PPN, or physical page number, and the valid bit will be 1. Okay. This is sort of like a cache miss, right? But the overhead of this miss is way bigger than the cache miss, because we have to access the disk. Okay, any question on page fault? And there will be a quiz about page fault pretty soon. So make sure that you guys ask. And all this is a translation, the sequence of the translation. Interesting. Right? Okay, if not, let me quickly talk about the miss penalty, right? In case we have a page fault, the miss penalty is going to be very high, right? For the conventional disk, right? It could be like 100 million cycles. Okay, for more than this, like SSD, this is lower, but still a fairly significant overhead. That's why we really don't want to miss, right? That often. We want to minimize the miss rate. And we do want to use a fully associated page placement scheme. And this is actually managed by OS. I'm going to talk a little bit more about this maybe next time. And this one is not going to be a single cycle, right? Placement. So OS software will be involved. It will take many cycles. But still, it's worth it, right? Since the penalty is just so large, right? 100 million cycles. It's just so large. And we want to use LRU, right? We're going to use a least recently used replacement policy, if possible, so that we can minimize the number of misses. All right, and OS, right? OS handles the page placement. The software is involved in this case. Okay, let me show you guys an example, okay, before we do the quiz, so that you guys appreciate what's going on with this address translation and also the page fault. Okay, so here's the page table. This is my page table. I only show you guys the first few entries, right? PT0, this one PT3, right? Up to PT3. The rest are not too important for this example. And I'm showing you guys a stream. This is time. Okay, this is time. By stream, I really mean this is a time sequence. Right? So we access this one by one over time. This is a sequence of virtual addresses in decimal. Okay. The question is, can you tell me like which access? Let's say we just read from these addresses. Right? Which access will lead to a page fault? Let's try to work on this. Okay. Before I ask you guys to do the quiz, quiz is very much similar. So if you don't understand this question, this problem, make sure that you ask. Okay, so this is the virtual address, right? It's a virtual address. And can you tell me what is the VPN? I don't even need to ask you like how many, right? How many? I don't even need to give you the number of bits, right, for the virtual address. So this should be actually obvious. What is the VPN? What's the VPN number in decimal? 128 is the absolute number of the virtual address. What is the VPN, guys? For the first one, 128, virtual address, virtual page number. Jacob already provided his solution. Jacob, what is the VPN for the very first one? Right, just in case it's not too clear from the page table, right? With PTE, and per entry we have valid bit, and if this is not valid, that means it's not allocated yet, right? There's no no useful physical page number. This is PPN, right? PPN. Okay, if this is valid, so over here this is valid, that means the PPN, right? The physical page number is 16. Think about the binder, right? Think about the book. The page number in the book, that's the VPN, right? The virtual page number. But when you put it in the binder, so in the binder, you also have right, many pages. So there you want to find, right, where exactly is the pages for the chapter for the heritage book, the 1000 book. So you need to find the PPN, the physical page number. That's where this page table is useful. Okay, so first 128, right? What is the address range? What is the address range for the very first page, very first virtual page? Guys, it's 4 kilobytes, right? Each page, 4 KB. Address range 0 to this number, right? 0 to this number. So any address within this range has a VPN of 0. Does it make sense? Does it make sense? Right? This is the very first page, right? And this page has this address range. So obviously, the first one has VPN, right? The VPN is 0. Any questions? You guys don't even need to translate it into a binary string, right? And then find the first, you know, the most even 20 bits or 10 bits, right? That's not necessary in this case. If this is clear, what is the VPN for this one? Maybe let's just talk about the page table. Now that VPN, okay, again, make sure you ask, right? Since I'll give you guys a quiz. VPN is 0, so that means we are gonna address this PTE, right? We use PTE, we use VPN to address the page table. VPN 0 means we are gonna address page table entry 0. Do we have a page fault or not in this case? Valid bit is 0. Yes or no, page fault? Yes, it is a page fault, right? Because valid bit is 0, we don't have anything allocated in the physical main memory. That's where we have a page fault. So there will be a page fault, right? And after this one, okay, then let me ask you about the second one, okay? And this is actually a very interesting discussion. What is the VPN for this one? Also 0, 2048, right? Also within this range. Okay. Also within this range. Second access, is this a page fault or not? Yes or no? No. So for those of you who are saying no, why is that? Can one of you unmute and chime in? If you're confident with your answer, that's a correct answer. The answer is no. The second access is not a page fault. Why is that? Valid bit is 1, so on. Why is that? Okay, but this is a good answer, right? First, when after we handle this access 128, right? We have already allocated, Emily, very good, right? We have already allocated, right? Some PPN, right? We have already moved the data, right, that corresponding page to the main memory. Since this is a sequence, right? And the valid bit now, the sound is also right. Now it's 1 after we handle the first page fault. So in the second access, we no longer have a page fault. Okay, makes sense? All right. This one, VPN 1. Okay, is it a page fault? Yes or no? No, because VPN 1, we access this PTE, right? We access this PTE. Let me remove this one. Just this is the PTE we access, and we get the PPN from here. Okay. Last one. VPN 2. Okay. Very good, right? The second page, starting from this, is it 2? Oh, right. The second page is from to this range, right? This is a VPN 1, the second page. Right? The third page, right? So this address is in the third page. So that's why it's a VPN is 2. And we need to access this address, right? This PTE. And we have a page fault, right? Is it clear? And this is a sequence, right? We have over here, there's a page fault, right? VPN 0, and this is valid bit 0. Second one, this is already handled, is no longer 0, so there's another page fault. And this one, we access this PTE, is not a page fault. This one is a page fault because we are accessing PTE too. Okay, when do the pages in the PTE change? When do the pages, Amanda, you're asking about the PPN? Right, in the PTE, we only have PPN, right? And the valid bit, right? So basically, this is handled by the OS, like I mentioned. Right? It's going to take many cycles. I'll tell you the exact sequence next time, okay, the next lecture. But this is going to take many cycles, million cycles, even in some cases, right? Before that, we will not, the processor will move on to other tasks. Okay, there's one more thing I want to discuss. Now we have been talking about the page placement, right? We want to minimize the miss rate, right? Because the miss penalty is just too high. That's why we want to do LRU, right? This least replacement, right? Least recently used. So though in the quiz, right, you guys don't need to worry about that. But later on, maybe in the homework and also the exam, you guys do need to worry about, right? So which one? So in case the whole memory, right? The whole page table is already, so all the bits are already, like all the valid bits are already one. You need to replace one. So you need to find the oldest one. But the thing is, since we have so many pages, in our case, right, in the example, we have 1 million pages. It's just too much, right, to do a full LRU, to do a complete LRU. We need too many bits, right? We need too much compute to compute which one is the oldest. So here's the workaround. Here's the approximation. So inside each PTE, the page table entry, so we'll just allocate one more bit called reference bit. If we access this page, okay, in recently, so we need to define the window by recent. Of course, we need to define the window. Okay, this window is defined by the OS. Right? If this within the right this window, right, recently this page is read or written, we'll just set this reference bit to be 1, meaning that this page is referenced. Okay, and OS will actually periodically set these variables to be 0. Right, so basically, if this page is not accessed in the last window, then the reference bit will turn 0. Okay. That's how the OS implements a sort of a inexpensive but approximate version of LRU. Okay. And also, it makes sense for write, right? We have been mainly focusing on read. For write, it makes sense to do write back, right? Instead of write through. Because we really don't want to access the disk that often. It's just so slow and just so expensive, right? And the thing is actually for more than, for most of the hard drives, actually, not just the more than hard drive SSD, there's a certain limit on how many writes that we can afford, right? We cannot afford, there's a real, right, a limit. We really don't want to write and also access this that often. So that's where we want to do write back. Okay, so with write back, we need the third bit, just like last time, right? So when we talk about this write back cache, where we have a third bit. Only when we evict, when we kick out corresponding cache block, or in this case, the corresponding page, that's where we write back. Okay, and also, there's a, right, so now we have been talking about these pages, right? Why do we, already mentioned that, why we use, right, why we have this spatial locality, right, for the pages. And also the other thing is, we don't really want to do the translation. If you look at the example that you guys are working on, like the quiz, so we don't want to translate the byte offsets, right? Because that's just too much of overhead. Right? We only want to translate the page, the physical, of the virtual page number to the physical page number. But even that one is a lot of work, right? We have 1 million pages. 1 million pages, and this page table is in the 1 million pages, 1 million PDEs, and this page table is sitting in the physical main memory. There's actually a problem. So I want to quickly discuss this problem. There's actually a bug. I would just say a bug, right? There's a problem so far. I hope that you guys have noticed this. Okay, we are dealing with a huge performance issue with this virtual memory scheme. What is that? Think about this microprocessor pipeline, right? We try so hard to break this pipeline, right? This numbers, break the compute, right, into a few stages, right, into several stages, and pipeline them, and then we realize that the access to the data RAM and instruction RAM is not fast enough, right? DRAM is too slow to access. So that's where we introduce cache, right? We introduce cache. So that's how we can get faster access to data. But can we use virtual address to access the cache? How can we find, when we try to find this instruction, when we try to find this data? What do we have to do first? Anyone? Do you guys see the problem? Now we are given an address, right? The program only has virtual address. The program only has virtual address, right? That's our assumption, and that's indeed the case. The program only has virtual address. The program cannot use the virtual address to directly access cache. The program does not have the physical address yet. What do? We have to go to the main memory. We have to find this page table to translate. Isn't that terrible, right? Isn't that terrible? Are we doomed? Right? I'm asking the same question again. Are we doomed? What's the fix? Any intuition? Any any ideas? Any suggestions? So this is something that we are going to discuss in the next lecture. But I hope that you guys, right, are aware of this issue. Right now, the page table is in the main memory, and we need to use it to do the address translation. But that means we need to access the main memory, the DRAM first, which pretty much contradicts whatever we have done so far, which basically canceled out, right, undermines all the attempts that we have made so far to improve the performance. Okay, so the real question is, how can we solve this? We're going to talk about this next time. All right. Okay, so we're done for this lecture. Make sure that you guys turn in your quiz.